Good afternoon, everybody. We are going to start our lectures on PHYS 111B, Introduction to Mechanics, Fluids, and Waves. Now, this is our first formal lecture, and we are going to discuss about the rectilinear motion in one dimensions. Let's share my PowerPoint. So this is the lecture notes. You can download it from the backboard. All right, let's start it. Now, first, we would like to have a very brief review on units and measurement. So in this course and also in most of the scientific studies, we are using the International System of Units. We call it SI unit. Now, SI unit is also called the MKS unit because it consists of three units with the prefix M, K, and S. Now, the base quantities for SI units in mechanics is the following. Now, there are totally 7 base quantity for SI unit, but in mechanics we only discuss about 3. Okay, and these 3 basis quantity are the length, mass, and time. Now, all other quantities in mechanics, they are made up of these 3 base quantity. So the 3 base square quantity form the basic. Okay, they form the foundation on which all other physical quantity are derived. And we denote the length by L, mass by M, and time by T. And the corresponding SI unit for this base quantity is, of course, meter for length, kilogram for mass, and second for time. And how about the derived units? Now, for example, Newton is a unit of force. I think you know it in your high school physics. Newton is actually a derived unit because Newton is actually defined by Newton's second law. We know that Newton's second law is F equal to ma, and the right-hand side is the mass times acceleration. The unit of mass is kilogram, and the units of acceleration is meter per second square. So the unit of force in SI unit should be the unit of mass multiplied by the unit of acceleration. And that gives me kilogram meter per second square. And we define 1 Newton as 1 kilogram meter per second square. So Newton is actually derived from the 3 basis unit, kilogram, meter, and second. Okay, and Joule for energy and work is also a derived unit. We know the formula for work is the force multiplied by the displacement. So we see that force, the unit of force is Newton, which is kilogram meter per second square. And when it's multiplied by a certain distance s, we have additional unit for distance. So the unit for energy or work, which is Joule, is 1 kg meter square per second square. Okay, because we have an additional unit of length here, so it becomes meter square. Now, I suggest you to review your textbook, Hardy, Resnick, and Walker, section 1 to 4 for unit conversion. If you do not remember it well, I suppose you know how to do it, but in case you don't remember it, I suggest you to review this part. Now we are going to teach you something new, and that something new is called order of magnitude estimation. Now, what is order? What is order of magnitude estimation? This is a method, essentially a method for us to estimate the value of a physical quantity correct to the order of 10. So what is the order of 10? For example, 10 to the power 2, 10 to the power minus 4, etc. They are the orders of 10. So the value that we are going to estimate is only corrected to that order. So don't expect that you can get a very accurate result. You can only get an estimate on how large the number is, about what is that order. For example, if I ask you, how many people are there in the stadium on a football match, then you may say there are you don't know the exact number. Then you say there are thousands of people. There may be several thousands of people. Then 1,000 is 10 to the power 3, right? 10 to the power 3 is 1,000. So the order of that number is 10 to the power 3. Okay, so it's easy to understand. So if you say any other numbers, you can immediately recognize what the order of that number is. So in this method, we are going to make a bold and simple assumption to do the estimation. So the bold means that we are brave. We are not afraid of being wrong. And we also make simple assumption. Although they are not accurate, but we still do that because we are not. We do not want a very accurate result. We only want to estimate the order. So that doesn't matter, right, whether the numbers are accurate enough. And we also make use of our common sense. For example, if you are asked about, say, the weights of a cup of coffee, you probably know that a cup of coffee has a volume of about 200 to 300 milliliter, which is about 200 to 300 gram. You will not drink a kilogram of coffee in the morning, right? You will not drink 10 milliliter of coffee in the morning. So the number, you have some idea about the order of that number. And for example, the population of the world, I think some of you may know that the population in the order of the world is of the order of 100 billion, right? So it's of the order of 10 to the power 9, okay? Sorry, of the order of billion. So that is of the order of 10 to the power 9, okay? I think about 7 or 8 billion. I don't remember the exact number. But if that is 8 billion, then 8 billion is already getting very close to 10 billion. I do not remember that exact number. I think you know better. But 8 billion, yeah, 8 billion should be of the order. I think should be order 10, because billion is of the order 9. So 8 billion is closer to 10 to the power 10. Okay. So thank you for correcting me for this point. You should also memorize some important numbers in physics, at least up to 1 significant figure. For example, the Avogadro number is 6 times 10 to the power 25. And the electronic charge is 1.6 times 10 to the power minus 90 coulomb. Those are the numbers that you might be able to remember. And we keep using basic physics equation, and we keep the calculation simple and to only correct to the lowest order. So some people, when they do this kind of calculation, they do not need a calculator. They simply do it in their mind. And sometimes your guesses may be wrong by a fraction, right? You may underestimate or overestimate something. But if you make this guesses for a large number of time, then sometimes you overestimate it and sometimes you underestimate it. And statistically, the error will be averaged out and the answer will turn out to be about right. So that is the miracle about this order of magnitude estimation. And so the idea is you just appreciate this is a powerful method, and please don't expect a very accurate result, but it is okay to get a correct order of something. Now, I give you an example. This is an example from a textbook. The largest ball of string, that means a ball that is made of string. This is the ball made of string, right? And the largest record, the record of the largest ball that is made of string has a radius of 2 meters. 2 meters is about the height of a door in your room, right? So a diameter of 4 meters is about twice that height. So you imagine that the string ball is very high, higher than floor, higher than your ceiling. So let's estimate the total length of the string that is required to make such a ball. Now, we make a bold and simple assumption. We simply assume that the string has a cross-sectional area. Don't tell me that the string has a circular cross-sectional area. A circle and a square doesn't really matter. They do not differ a lot. And also, I assume that the width of the square, the length, the side of the square is 4 millimeter, and there's no space between the string in the sphere. This is obviously not correct. Okay, you might be wrong by a factor of 2, something like that. But I just made this bold assumption just for the sake of guessing. So the length, the total volume of the string is the cross-sectional area multiplied by the total length of the string, right? The cross-sectional area is a squared, the length of the string is L, and the volume of the sphere is 4/3 pi r cubed, where r is the radius of the string sphere. And so we equate the two volume. We assume no space between the string, but that is not true, obviously, but we still assume that, and we can solve for L. And so we put in all the numbers that we have, and we got the number of 2 to the power 6, 10 to the power 6 meter. So the order of this number is 10 to the power 6 meter. How long is 10 to the power 6 meter? 1 kilometer is 10 to the power 3 meter, is 1,000 meter, right? So 10 to the power 6 meter is what? It's several thousand kilometer. Now, several thousand kilometers is a very long distance. Suppose you go from Hong Kong to India. The distance between Hong Kong and India is about, I think, about 3,000 kilometers. So it requires several thousand kilometers of string to make a string ball of heights of diameter 4 meter. Now, you couldn't have imagined that before you do the calculation. It is quite unexpected. Now, I'm not saying that I have a very good accurate result. It could be 1,000 kilometers or 2,000 or 3,000. I don't know what exactly the number is, but at least I have an idea of how large the number is. Okay, so that I get an order, I get a sense of the order. That is the purpose of this estimation. Now, for example, you can do it your homework. I will give you another homework otherwise, but you can always do it yourself. Estimate the number of molecules in a cup of coffee. Now, as I say, that a cup of coffee is about that you drink in the morning is about 200 to 300 grams in weights, right? So assume they totally made of water. So how many water molecules are there? You can make a simple estimation of that. You can first find the molar mass of water, and then using the total mass of the cup of coffee, you can estimate how many particles are there. Okay. Yeah. That's you are correct. Okay. Somebody already in 80 grams is that number, right? So you can easily find the total mass, total number in the column. Okay. Now you may ask, what is the use of that? We only get the correct order. So what's big deal about that? Now the answer is that before physicists find the correct mechanism to a physical phenomenon, they always do a order of magnitude estimation. Okay, the order of magnitude estimation actually help physicists to find the correct mechanism so that they can study more and create a more precise model of that mechanism to explain a particular physical phenomenon. Now, let me have an example for you. In the late 19th century, people are wondering why the sun shines. Okay, what power the sun shines? Okay, what is the energy sources of the sun? Some people say, like for example, a person called Kelvin, he said that the sun shines by contraction because the sun contracts under its own gravity, so it can convert its gravitational potential energy into heat. So when the sun contracts, it heats up, and the heat is eventually converted into radiation. So this is his theory about the contraction of the sun to that support the energy output. But you can really do a very simple order of magnitude estimation. Given the current, the mass and the brightness of the sun, we know the energy output of the sun. The contracting gravitational potential energy can only sustain the energy output of the suns by several tens of millions of years. That is 10 to the power 7. But we know that because of our first fossil record, that the Earth has exists at least for several billions of years. We now know that the Earth exists for 4.6 billion years. So the Earth cannot be older than the sun, right? So the sun must also exist at least for several billions of years, which is much longer than this several tens of millions of years, right? 10 to the power 9 is 2 order of magnitude larger than 10 to the power 7. So this theory that the sun shines by contraction must not be true. That is the wrong mechanism. So later on, scientists found that the sun generates energy actually by nuclear fusion. And by doing a simple order of magnitude estimation, they found that the nuclear fusion inside the sun, which fuses the hydrogen into helium, is enough to sustain the energy output of the sun by at least several billions of years. Okay. So try to think like the physicists. This is how physicists identify the correct mechanism of a physical phenomena. I tell you something interesting. Enrico Fermi is a very famous physicist. Okay, he's good. He was good both in experimental physics research and theoretical calculation. He excelled in both. And he have one very strong skill is to do the order of magnitude estimation. He's very good in doing that. And legend has it that during the first explosion of the atomic bomb, they have a test explosion of the atomic bomb in the desert in the United States. So Fermi stand at a distance of several kilometers from the site of explosion. And during the explosion, there are shock waves coming out from the exploding bomb, and the shock wave just passes, just like some wind, just fly passes his body. And during when the shock wave come, Enrico Fermi, he held a few pieces of paper, small pieces of paper, and it dropped it down. So when the wind passes, it blew it deflects the falling motion of those small pieces of paper. And from the angle of deflection, and after a few minutes of mental calculation, Enrico Fermi is able to find that the explosion energy is of the order of 0.01 megatons equivalent of TNT, the explosive power, 0.01 megatons of explosive. Okay, so that is really a story. Okay, nobody exactly know how he did it, but there's some speculation about how he did it. You can find it on the web if you like. Okay. Now I'm going to teach you another also interesting method called dimensional analysis. So what is the dimension? The dimension is a type of the base unit that makes up a physical quantity. As we say, the mass has a unit kilogram, the length has a unit meter, and the time has a unit second. So the mass has a dimension of m, and length has a dimension of l, and the dimension of time is denoted by t. So m, l, t denote the dimension of mass, length, and time respectively. And for example, if you are talking about a surface area, the area has a unit of meter square in SI unit. So that means the dimension of the area is L squared. It's a square of the length, right? Now, we use a square bracket to denote the dimension of a physical quantity. If we put that quantity inside the square bracket, what we mean is that we are checking, we are finding the dimension of that quantity. And velocity, the unit is meter per second, right? So the dimension for the velocity is distance per unit time. So it's LT minus 1. And the dimension unit for acceleration in meter per second square. So the dimension for acceleration is distance per time square. So LT minus 2. Okay, so these are the dimension for the common physical quantity. Now, a physical equation always says that the right-hand side is equal to the left-hand side, right? We have both sides of an equation. When we say that the left-hand side is equal to the right-hand side, we are comparing the same thing, right? We cannot compare an apple with an orange. When we say the left-hand side of the equation is equal to the right-hand side, that means we are comparing the same quantity and they are equal. So they must have the same dimension, right? A mass cannot equal to a length, and a time cannot be equal to a mass, right? If the two quantities are of different dimension, it is not meaningful. It is meaningless to say that they are equal. So in order for physical equation to hold, the dimension of the two sides of the equation must be equal. Okay. Now, so the equation that is dimensionally correct does not imply that it is correct. But if an equation is dimensionally not correct, then the equation could not be right. Okay, it must be wrong. Okay, so that is the basic criteria for physical equation to be correct. Now, so let's take some common example you learned in high school. I think you learned this formula. When you drop a mass m, when a mass m fall at distance, a vertical distance h under gravity, the change in potential energy is mgh, and that energy is converted to kinetic energy, which is half mv squared. So by conservation of energy, half mv squared is equal to mgh. So after canceling the mass m, we have b squared equal to 2gh, right? We look at this equation. The left-hand side has the dimension of b squared, okay? And the dimension of v is LT minus 1. So we square it. So the dimension of v squared is L squared t to the power minus 2. That is the dimension of v squared. And how about the right-hand side? The 2 does not carry a dimension. It is only a number. So the dimension is the dimension on the right-hand side is the dimension of g multiplied by the dimension of h. The dimension of g is, because g is the acceleration due to gravity, so it has a dimension of LT minus 2. The dimension of h is, of course, L. So again, when the 2 multiply together, we get L squared t to the power minus 2. So it is easy to see that the two sides of the equation have the same dimension. Okay, so that is a very simple example. Now, I urge you to do this in your homework. This is in fact in part B of your homework. So you don't need to submit it, but I suggest you to do it. This is a very simple example. Now, dimensional analysis can help us find the correct form of a physical equation. Okay, that is quite unexpected. Even though you don't know how to derive that equation, you can still, in some cases, you can still use dimensional analysis to help you find the correct form of that equation. For example, this is a simple pendulum. There's a pendulum board here. It is suspended from a fixed point by a string of length L. Okay, so we have a length of the string to be equal to L, and the mass of the bulb is m. And because the pendulum is swinging back and forth, it is affected by the gravity of the Earth. So we expect that the period of the oscillation, the time required for the bulb to oscillate 1 period, should be dependent on the acceleration due to gravity, because it's affected by the gravity of Earth. It may be dependent on the mass of the bulb, m, and it also may depend on the length of suspension L. Now, those are the parameters that we can think of. We don't know if we can exhaust all the possibility, but those are the obvious parameter. The pendulum, the period of the pendulum may depend on those parameters. So we postulate an equation of this form. We postulate that the period of oscillation, that is the time for the pendulum to oscillate one period, to oscillate one cycle, is proportional to the length of the string to the power alpha, the acceleration due to gravity to the power beta, and the mass of the pendulum bob to the power gamma. And the constant C is dimensionless. Okay, it is only a number. It does not carry a dimension. So obviously, the left-hand side is a time, right? So it carries a dimension of time because we are talking about the period. And the right-hand side consists of three quantities. The C does not have a dimension, so it becomes the dimension of L y raised to power alpha, dimension of G raised to the power beta, and dimension of M raised to the power gamma. The three quantities multiplying together will give you the dimension of time on the left-hand side. Okay, so dimension of the length L is of course big L to the power alpha. G has a dimension of LT minus 2 as before, so it's raised to the power beta, and M has a dimension of M raised to the power gamma. So we group all the terms with L together. So this is L to the power alpha multiplied by L to the power beta. So I have L raises to the power alpha plus beta. And this quantity is raised to the power beta. So the T minus 2 become T raises to the power minus 2 beta. And we also have M to the power gamma. Okay. Now, the fact that the dimension of both sides to be equal means that this three quantity, when they multiply together, should give you a dimension of time. So what should be alpha, beta, and gamma? I immediately realized that gamma should be 0, because otherwise there would be no way for us to get rid of the mass, because the left-hand side does not contain the mass. So the right-hand side should not contain the mass, right? And the only way that you can get rid of the mass is that you don't have that dependent. And you don't have that dependent means that the gamma is 0. And also the left-hand side should not depend on length, right? Because the right-hand should not depend on length because the left-hand side do not have the length. And so alpha plus beta must also be 0. Is that right? And to match the dimension of time, you must have minus 2 beta equal to 1, right? To make the dimension on both sides equal. So by listing out these three equations, you will be able to solve alpha, beta, and gamma easily. And you can look up what the constant C is from the internet or from your textbook. So please complete your homework. I give you the solution, but I suggest you to do it before looking at the solution. Now, if you want a more thorough discussion on the physical law and the so-called natural units, there are actually some reason to use the natural units. We can actually get rid of all the constant in the equation by using some special units that is called natural units. And you want to have a different understanding of this methods, then you should look at the e-learning module listed here. Now this is beyond the syllabus, but I suggest some of you who might be interested, suggest to you in case some of you might be interested to learn more. Now then we come to a real description of motion. We come to the kinematics, and we described the kinematics using differentiation, using the mathematical tools of differentiation. Now there are two words commonly encountered. We commonly encounter two words in mechanics. One word is kinematics. The other word is dynamics. So what is the difference between kinematics and dynamics? Do you know that? Now, as I say here, Kinematic is a pure description of motion. You only described how the object moves using certain physical quantity. Those physical quantity include, for example, displacement, displacement you learned in high school, velocity, and acceleration. These are the quantity that helps you describe how fast the body moves and its position, and also how fast the velocity may change, right? And then using this quantity, we set up some equation to describe the motion. For example, the equation for uniformly accelerated motion, V equal to U plus AT, you learned in high school. So that is a pure description of the motion without involving the force. In this equation, we don't see the force, right? So we only learn how to describe it, but we don't know what causes the motion. The causes of the motion is not expressly mentioned here. But for dynamics, if we talk about dynamics, what we say, what we want to interested is the relation between force and motion. Is the cause, what causes the motion? That is the question that we are interested in dynamic. For example, Newton's second law is a dynamic equation. It relates the acceleration of the object with the force, with the net force acting on that object. And the force may come from different sources. It may come from gravity. And for a badminton court like this, it may be strongly affected by air resistance. So the total force F, the resultant force F, may be the sum of the gravity force plus the air resistance. Okay. And so if you trace the motion of a badminton court in air, it might look like something. This trajectory might look like something like this. This is the position. These are the position of the badminton court at different times. Okay, this is a schematic diagram only, but you see that this trajectory is not symmetric because of the effect of air resistance. Okay, now if I only know the position of the badminton court at any time, and I know how fast it's moved, etc., then I am describing using the language of kinematics. But if I relay the acceleration of the badminton court with gravity, with air resistance, using Newton's second law, I'm doing the dynamic. Okay. Now let's start with a very simple example of displacement. Suppose we now are interested in a rectilinear motion in which a person moves along a straight line back and forth. So at time 0, at a certain time, I call it T1. The position, I draw an x-axis here, which is positive to the right. And so at time T1, the person is now at the position 3, which I denote by x1. So I count this distance. I measure this distance of the person from the origin. And this is the value x1 I got. And at another time, the person has moved to another position. And he's now at a distance of 5 meters, say, from the origin. And I call this new coordinate x2. Okay, so I'm interested in the change in position. And the change in position is x2 minus x1. And formally, we call that the change in displacement. Okay, the displacement has a direction. And in these simple cases, the person is only allowed to move forward and backward. So the direction may be denoted by a sign in the displacement. So the change in displacement is the final position minus the initial position. And changes take place in a time interval delta t, right? The change is delta x, and that change takes place in a time delta t. And delta t is, of course, the final time minus initial time, which is t2 minus t1. Now here we define, the first thing is that we define the positive direction. And so the position carries a sign. And for simplicity, we may usually take t equal to 0 at the starting time. Okay, this is not a must, but it makes the equation sometimes more convenient. Now suppose the person is not on always on the right of the origin. He sometimes he start from this position, which is left of the origin. So at this position at time t1, his position is denoted by -1, because the minus sign denotes that he is left on the negative side of the origin. So x1 is -1. At another time, he is at x equal to 3, where he now goes to the positive side. So the difference between x2 and x1, x2 minus x1 is 3 minus 1. So it's 3 plus 1 is 4. Okay, so this is a change in displacement. Now, in doing the calculation, we always follow that formula. The formula tells us that if I want to find the change in displacement, I always use the final position minus the initial position, or the final displacement minus the initial displacement. I always follow that formula. And the sign will take care of the direction. Okay, so I just plug in all the numbers together with the sign to the equation, and the equation simply will give me the right number. Now the equation says that the change in displacement is 4 meters. Okay, and the number 4 meters being positive, it means that the person has now moved along the positive x direction by 4 meters. Okay, the direction can be inferred from the sign. I don't need to think about the direction during a calculation. In a calculation, I only have to follow that formula and put in the number. Okay, and from the displacement, if I know the displacement of the person versus time at different time, I can derive the velocity. And from the velocity versus time graph, I can derive the acceleration versus time dependence. So that is how we work on kinematics. So what is velocity? Velocity is the rate of change of displacement. And we are interested, for example, in the average velocity over a period of time. Suppose in a period of time delta t, the object has changed its displacement by delta x. So we divide delta x by delta t, and this is called the average velocity. We denote the average velocity by the subscript AVE. AVE means average. So as the name suggests, this is not the instantaneous velocity. It is only the average over a period. Even though if the period is the period may not be long, but inside that period of time, the velocity of the object will still change. So this is only an average quantity over a period. It does not represent it may not represent the velocity of the object at a certain time. Okay, it is only an average of the velocity over a period. Now, if you look at the graphical representation, that becomes more clear. If I plot the displacement x of the object versus the time t, then it may result in such a curve. Okay, this is a hypothetical curve. That's the displacement change with time. So in a time interval delta t, the object has changed its displacement by delta x. So the horizontal blue line here is delta t. The vertical blue line is delta x. So the average velocity is defined as delta x over delta t. And you can immediately visualize that by using this triangle. You can immediately see that the quantity delta x over delta t is actually the slope of the red line. That is the line joining the initial point and the final point. Okay, so this is the slope of this red line is equal to the average velocity. But in mechanics, in kinematics, we are not satisfied with the average value. We want to know the velocity of the object at a particular time. Even though it is changing, we want to know exactly what its value is in a particular time. So that is called the instantaneous velocity. The instantaneous velocity is actually the average velocity of an object over a very, very small period of time. And technically, if you go to the mathematical department, they will tell you that this is an infinitesimal small period of time. That is tends to zero. That period of time is very small and that tends to zero. And if that is the case, then my ratio of delta x over delta t in that limit, in a limit where delta t tends to zero, will become the instantaneous velocity v. And we formally denote this limit by the derivative of x with respect to t, and we write as dx dt. Dx dt is not a fraction, okay? Dx dt is an infinitesimal small change in displacement over an infinitesimal small time interval, okay? So that is a limit between the ratio of a change in displacement to the change in time interval, okay? Now let's look at the graphical representation, okay? Report the xt graph again, and I think you see this is delta t and this is delta x. Now it becomes the blue line, right? And delta x over delta t is the slope of the yellow line. Is that right? That is the average velocity. Okay. Now imagine my delta t tends to zero. When delta t tends to zero, this point is getting very, very close to the original point. The 2 points are getting closer and closer together, because now we consider a very small time interval. So the point here is getting closer to this point. The 2 points becoming almost merging together. Okay, so imagine that when these 2 points are getting sufficiently close, the yellow line, the slope of the yellow line will tend to the slope of the tangent to the curve at this point. The red line is the tangent to the curve. It is tangential to the curve. So when the 2 points are very close together, then the slope of the yellow line, that is the average velocity, will tend to the instantaneous velocity, which is represented by the slope of the tangent to the curve. So the geometrical interpretation of the instantaneous velocity is simple. It is simply the slope of the tangent to the curve at the time t. Okay, now this expression is exact. It tells you the slope at a certain, tells you the velocity at a certain instant. Now, but if my delta t is not exactly zero, but if my delta t is small enough, I can still use the ratio of delta x over delta t to approximate my instantaneous velocity. Now I write an approximate sign here because this is not exact. The only exact expression is that we imagine that the dt to be extremely small. That is infinitesimal small. That is the only way for us to reach this limit. Okay, for all other finite delta t, I cannot write this an exact equality. It is only approximate. But for practical purpose, if I have a small enough delta t, I can always approximate my instantaneous velocity at delta x over delta t. Like for example, if these 2 points are getting very close, the yellow line becomes the red line. Okay. Now, why I say that? The mathematician may not be happy. Why do I say that? Because this approximation method is actually very useful, especially when we are trying to do numerical method. We are going to introduce to you how to use computer to solve a physical problem. And in those situations, we would approximate the instantaneous velocity by a finite difference. We write the instantaneous velocity approximated as a finite difference, and we iterate the equation step by step forward to solve the whole motion. That is what we are going to do next. Okay, so bear in mind that this is a good approximation when delta t is small. And so what is acceleration? Well, acceleration is the rate of change of velocity. And again, we have the average acceleration. That means the change in velocity over a certain period of time. Delta v over delta t give you the average acceleration. So let's have a graphical representation. Now we are plotting the velocity against time, but not the displacement. Note that this vertical axis now is the velocity. So we assume the velocity change like this. And so the horizontal blue line is the delta t, and the vertical blue line is delta v. So delta v over delta t is the slope of the red line, the line that joins the 2 points together, straight line that joins 2 points together, right? So this is a graphical representation of the average velocity, of the average acceleration. Sorry about that, because we are now talking about acceleration, okay? But again, we are interested in the instantaneous value. So we define the instantaneous acceleration as the average acceleration over infinitesimal small period of time. So we take the limit delta t tends to 0 and delta v over delta t become dv dt, okay? And that is the derivative of the velocity with respect to time. And the graphical representation is similar to that of the displacement. Delta v over delta t represent the slope of the yellow line. But if my delta t tends to 0, the 2 points here become very close together, and the yellow line become the red line, which is the tangent to the curve. So the instantaneous acceleration is just the slope of the tangent to the curve, to the VT graph, okay? And again, if my delta t is not infinitesimal but sufficiently small, we can still approximate the instantaneous acceleration by the ratio of delta v over delta t. Okay, and that again form at the basis for the numerical method that I will introduce to you later. So let's take a break of 10 minutes. And after the break, we are going to talk about how to actually solve a kinematic problem. So we have a break here.